Okay, so thanks very much for the invitation. I already enjoyed a few days here last week teaching a wonderful group of students. I thought I'd take this opportunity to focus on a few recent projects that we've been doing that are really in tune with the theme of this workshop and the whole program. This is our past light cone. You're all cosmologists, so I won't take you through it in detail, but the point is that we have a large number of observations in cosmology, and what we see in the sky is full of information. And we're beginning, of course, to explore a number of these observables here. But next decade cosmology will be uncovering many more of these modes. So essentially we'll start getting a fairly representative census of all of the fluctuation modes in the universe. It will be a decade of surveys. I should also say that, of course, talking about next decade cosmology is fairly safe, given that we're in 2019. It's not too much of a stretch and too much of an extrapolation. But it is true, therefore I can state with confidence that it is a decade of surveys where the exponential increase in number of modes that we've witnessed, both in the cosmic microwave background and in various probes of the large-scale structure, the density distribution of structure in the universe, is going to continue to grow exponentially. And several people in the audience here, of course, are responsible for or allowing us or enjoy, we can thank them for pushing this exponential further. So the themes of cosmology in the next decade, to me, the three main fundamental cosmology themes are probes of the beginning. So Dick was in that theme in his talk. B-modes, tilt, running, the average cosmic density, that's something we really want to know in detail. Dick also focused on another topic that's close to my heart as well, non-Gaussianity. We want to probe the particle content. There's still significant mysteries about what the physics of dark matter is, for example, whether it might even not be a particle, but if it is a particle, it could be very light particles that may or may not be the dark matter, and we still haven't resolved the neutrino mass. And cosmic acceleration is a mystery that I think deserves its own bullet point in that list, because we really don't understand what is making the universe accelerate. We usually call this dark energy, but it's just a label. Maybe not so much in fundamental cosmology, but still, of course, very important, is the study of the cosmic history that ties all of this from the first stars, first black holes, first galaxies until today, which is very important to understand also in order to make progress on these issues here. So what will be different in the next decade from this decade? Well, we will get access to these new scales, new modes, which just have a larger amount of data, higher resolution, deeper surveys, more events. This is going to push our knowledge and also our capacity to analyze these data. We will look at new observables that have just recently come up, gravitational waves as cosmological probes, spectral distortions, hopefully in more detail than we've been able to do so far, and other channels that will give us cosmological information. And this means that we will reach, both of those together means that we will reach a new level of complexity. We have to model not just the actual signals, but also the foregrounds and all kinds of systematics, and we have to understand them. And Dick very, of course, correctly emphasized the dependence of various multiple cosmological probes that also have to be modeled. So we don't just need new data, we don't just need new theory ideas in the category of fundamental cosmology on the previous slide, we also need new approaches to deal with this kind of complexity. So how do we deal with cosmological complexity? So I like to categorize this in three categories, three strategies. One is you avoid them. So you just do linear physics. You go try to do the cleanest possible experiment. That is great, but somewhat limited. The most common approach is to try to adapt. You try to pick smart summaries of the data that are maybe robust to certain kinds of systematics or certain instrumental effects that you don't fully control. Or then there's what I like to call the attack approach, where you push your computational inference through with as much physics as you can throw at the problem, and you model the data forward. And in real life, of course, there's always going to be some combination of those three, depending on your personality, preferences, and so forth, tastes. So let me just focus on two themes. I'll see how far I get. Certainly the first one, which is a new approach to classical cosmological tests. So I'll focus on new approaches on things that maybe we thought we already understood. So classical cosmological tests, and also to the problem of weak lensing. There's a third theme, which I will not talk about, which I would highlight Shubhadeep Mukherjee's talk. He will talk on Wednesday about a third category of tests here using gravitational waves in cosmology. So this first section, start off, these are my collaborators, a couple of papers you might want to look at. So let's do Cosmology 101. Okay, if you want to do new approaches, start at the beginning. You open up your textbook, Cosmology 101. What's the first chapter? The first chapter is Homogeneous and Isotropic Universe. Okay, so you leaf through it. Chapter 1.1, there's the Friedmann-Lemaitre-Robertson-Walker metric. There's the Friedmann equation. There's the Ricciarduri equation. Okay, all the various equations. Classical cosmological test, chapter 2. Okay, so typically one of the first ones mentioned is the luminosity distance redshift relation. How do we test that? Well, you typically read something like you observe an object's luminosity and its redshift, and then you do that for many objects, and you plot that one against the other, and so you fit that to your cosmological model. Well, depending on where you are as what your level of pedantry is, let's put it this way. You might say, hold on a second. We've been talking about a homogeneous and isotropic universe. There are no objects in a homogeneous and isotropic universe. So how can I be expected to measure luminosity distances and redshifts to things, because there are no things? So we need to consider structure. Okay, let's see if we can approach the same kind of thing, but from a different perspective. We want to consider structure in the universe. So a new way to think about, for example, the luminosity distance redshift relation is to consider two types of tracers. So now I introduce structure. Okay, now there are fluctuations in the universe, a bunch of tracers. One luminosity distance tracer, which just completely arbitrarily I might call Sn. Another one, a redshift tracer that I might call G. And let's write down the absolutely simplest possible model for their densities. So the Gaussian PDF, this is the log, okay, -2 times the log of that. So here's the sort of chi-squared term, a determinant term. Okay, that takes the density of this redshift tracer, so for example galaxies, density of the luminosity distance tracer, for example supernovae, and just this is a Gaussian model for that. Okay, so let's look at this this object here, this covariance. Okay, here I've just copied the same thing. If we assume that both of those tracers cluster in some way, okay, there's structure in the universe, and we think of them as being mapped. Let's both of them live in co-moving space to start with. Okay, they both cluster isotropically and homogeneously in co-moving space. But then we actually observe them in luminosity distance or redshift. So there's going to be this transformation from co-moving to redshift or co-moving to distance, which is cosmology dependent, parameter dependent. So this covariance in this model will look like this. It's going to be the isotropic homogeneous correlation or covariance of these tracers and their cross correlations, and then the mappings, onto the space where we actually observe them. Okay, so far so good. What does that do for us? Well, if we look at this a little bit longer, we realize that actually one of these blocks here is just a different way of writing the Alka-Pyczynski test. So if we do analysis using just these galaxies, just the redshift tracers, and note that we do not consider the covariance here as a function of cosmological parameters. We just fix them. Okay, we put a fiducial model there. We don't vary that. That is, the Alka-Pyczynski test basically says, let's vary this transformation as a function of cosmological parameters until I get a good fit to the data, meaning until I isotropize the data. Okay, I can sort of shift the galaxies around as a function of this mapping and make them as isotropic as I can, because this is an isotropic, and I will achieve the best fit because at the point where I isotropize them as much as possible, because the cosmological principle tells us that the universe is homogeneous isotropic statistically. Okay, so we found an old friend here. Let's go to this one. Well, this is actually a new kind of Alka-Pyczynski test. Same thing, except you don't do it in redshift space. You can do it in luminosity distance space. As far as I know, this has not been pointed out yet, that you can, if you have a bunch of supernovas and you just have them in luminosity distance, you don't even need their redshifts. As long as you know their distances, you can then do another cosmological test. As far as I know, is not commonly known or commonly discussed. But then, of course, there's also this off-diagonal term here, which is a new kind of generalized Alka-Pyczynski test, which is a cross-correlation Alka-Pyczynski test. So what does this do? Okay, this thing here has takes all pairs, right? I mean, both directions, all pairs of distance tracers and redshift tracers. So it's a sum over all pairs. Actually, I'm going to skip over the next two slides. They just review the Alka-Pyczynski test, just pointing out that Alka-Pyczynski is about standard spheres. You basically change the cosmological parameters in such a way that a sphere looks like a sphere when you map it into co-moving. And it's very sensitive to the Hubble constant, which is great because that thing is very sensitive to the properties. I mean, it's directly tracing the expansion history of the universe. There are no extra integrals between. And so what we have here is this cross-correlation Alka-Pyczynski test, which actually is part of this multi-tracer AP test. When you take all of those together, they involve the sum over all of these pairs. And then you let's do the following. Okay, we just assumed a covariance. We said we'd take some fiducial covariance. Didn't have to take the correct one. Okay, but let's take a kind of far out there one. Let's assume that the covariance is diagonal. Okay, so that is what you have white noise fluctuations, which we don't. But let's say we did that. Then this sum over all pairs suddenly collapses into a sum where you get only those objects that have both luminosity distance and redshifts attached to the same object. If I make these diagonal, then I only get a linear sum over the same object if it's both a distance and a redshift tracer. And that gives me back the classical test. That's what you do when you measure a bunch of objects, assign distances and redshifts to them. But this tells us that, in fact, that is a horrendous approximation to what you should be doing. I mean, maybe not horrendous, but it is certainly not an optimal way of proceeding, because you could actually take all of the pairs and change your cosmology to isotropize the correlation function. So this insight can be used to build new methods for cosmology for the next decade, especially supernova cosmology. So where we will have tens of thousands of supernovae, maybe hundreds of thousands of supernovae. Those are far too many to all follow up spectroscopically, so we have a lot of distances, but not necessarily redshifts to them. And attempts to estimate their redshifts using only photometry, not having spectroscopic follow-up, leads to type contamination and all kinds of systematics. So the point is that rather than just measuring distances and redshifts to all these individual objects, in fact, you recognize that they're embedded and both trace galaxies and supernovae, and the supernovae themselves, most particularly, trace the underlying density perturbations in some way. And we can exploit that. So there both supernovae and galaxies are biased traces of the density field. Their cross-correlation is homogeneous and isotropic and a function of the cosmological parameters. And so you can estimate cosmological parameters by maximizing the correlation and the isotropy. So when you do that, you find, so here just some forecasts for relatively conservative parameters. Well, let's say parameters that are intended to be representative of LSST once it gets to 50,000 supernovae, and with a redshift survey of 20 million galaxies, like DESI, for example, which would roughly be occur at the same time. And so one of the striking features of this plot is that this here is if you had redshifts, spectroscopic redshifts for all of these supernovae. And the dashed line is actually if you don't have spectroscopic redshifts for the supernovae, you just have the galaxies to cross-correlate. And it turns out you don't, and you can even get better. So by these constraints are a function, thank you, are a function of at what scale you cut off. And in fact, we cut off at a very, very conservative scale, which I'm happy to explain later why this is actually very conservative. And it turns out you can actually get better results from this than if you did the kind of perfect case standard classical luminosity distance relation. Okay, so very good. We have a new approach to do supernova cosmology with next generation surveys. Let's go back and look at this term here, this on-diagonal term. Instead of just modeling the correlation function, which is what I've written here, because I've written the simplest possible model, just a Gaussian model, can we model the full statistics of the density field and do again, a generalized Alcock-Paczynski test where we improve the classical Alcock-Paczynski test. So the idea is to start with these initial fluctuations that Dick was talking about, okay, that he calls zeta, some various ways of various notations for that, but this zeta map, let's say, and you map it forward nonlinearly into the density field, into the observed galaxy distribution, which is nonlinear and non-Gaussian. And many of you maybe have seen me talk about this approach for doing that. I'm not going to go into the details of it, just to point out that there is a way of doing a full forward model of nonlinear density fields of galaxies, biased galaxies, for a real survey, which can then be explored, and you can actually make maps of the initial conditions. You vary the initial conditions as parameters, and you keep the final galaxy locations fixed. And so that's another way, similar to what we do with the cosmic microwave background, except there the problem is linear, where we go back and reconstruct the conditions. Here we can do it from large-scale structure, nonlinear large-scale structure data. I'm going to skip this movie due to time constraints, but this shows what kind of constraints you can get on these initial conditions. This is from the Sloan Digital Sky Survey, actual data, okay, with galaxies here, the reconstructed density field today, and here's the reconstructed density field in the early universe. Of course, we have the full history of the evolution of the universe for every single sample, because we have initial conditions, we have the dynamics, we know all the velocities and positions of all these particles at all times, and you can see that they hit where the actual galaxies sit at the current time. But one of the challenges for this approach has almost been that it's too successful. It has so much statistical power that when you get the forward model just slightly wrong, you can bias the cosmological inferences if you take all of this information. So what you need to do, because the galaxy dark matter connection is probably the most complicated part of this, is you want to decouple the galaxy bias model from the cosmological parameters somehow. And so the insight is that if you build in the cosmological parameter dependence only in the mapping of co-moving to redshift space, and you actually don't consider the variation with the structure, so the power spectrum dependence, then you get an Alcock-Paczynski test, except not for a Gaussian model, but for a fully non-Gaussian, I mean, a significantly non-Gaussian model. So you're doing Alcock-Paczynski not just at the 2-point, but also the 3, 4, 5, 6, 7, etc., all the endpoint functions. Okay, so when you do this, this is described in this paper here, and you vary the cosmological parameters until you isotropize again the distribution. And you get extremely high precision inferences. So you know, for a Sloan-like survey, you actually get, because you use all of them, you just use a ton of modes and you model them accurately, you get extremely high precision inferences. So the question is, are these robust? Can you believe them? And it turns out that, so here's a plot of the cosmology block in the full covariance matrix of all of our bias parameters and the cosmology, and you see that for this approach, the cosmology decouples almost entirely from the bias model. And we've demonstrated that when you choose the wrong cosmology, you still get the right answer, because when you choose the wrong power spectrum, you still get the right answer for the cosmology, because basically the choice of cosmology is just a way of setting the weights of your inference. Okay, I think I'm probably out of time, so I'm going 1 minute. I was going to talk about a new approach to CMB lensing, which we all know is this effect, of course, where you distort the background, and most importantly, that is very interesting in itself, but produces a significant foreground for B modes on large scales, or actually also intermediate scales, lensing, where the lensing B modes are important. We've detected it at very high significance now, but we need to go beyond. Again, it's the case where the methodology needs to change if you want to really benefit from upcoming surveys. And this has been a problem that's been around for about 20 years. Turns out that the various attempts to do something more optimal have failed. And only very recently, two groups, group with Anthony Lewis and Julien Caron, and us have found ways of breaking through this. Our approach has been to look at lensing again in a completely different way. So rather than taking the lensed sky map and thinking of it as an expansion in terms of the small lensing parameter, the sub-Taylor expansion approach, instead you can think of lensing dynamically. You can think of the sky positions being distorted dynamically, and you can write down a differential equation, a dynamical equation. And then these 0 to n now are not orders in perturbation theory, but they are steps as you solve the differential equation. This is an evolution operator. So from your Hamiltonian dynamics, you might remember this. Okay, you have an evolution operator that advances the state of your system, and you can write this down. This is just the magnification matrix here, for example. That's the analogous quantity to the momentum in that problem. So when you do that, it turns out the thing that has been holding up this field, which is this horrible lensing determinant, actually is conserved. You can write this as a conserved flow and show exactly that it conserves the lensing determinant, as long as you take enough steps. This is a pedagogical point of what the difference between those two approaches is, but let's just show the result real quick, given the time. So you can use this to de-lens. So this is E mode contaminated B mode, that after a few steps in this algorithm that solved the inverse problem using the lens flow algorithm as the forward model, and you construct the lensing potential and the B modes very accurately. Here's the comparison of the truth, simulation ground truth, and the reconstruction. The fact that they don't look exactly the same has to do with the fact that the instrument isn't zero noise. And so this is exactly what is expected for the setup that we've used, which is like the S4 CMB stage 4 missions that are coming up. You get, depending on, the lower the signals, actually the higher the signal's noise, the better the higher the improvement in this kind of approach compared to the standard approach. And here I just wanted to show some preliminary results on what you can do in terms of the B mode reconstruction. So this is the true lensing potential, true E mode, true B mode that goes into the problem. And here are the reconstructions of B. which of course is caused or created by paramolecular gravitational waves. And we're now able to explore these high-dimensional problems, reconstruct these maps, propagate all the non-Gaussian uncertainties and so forth for this problem. So this will come out shortly. So let me conclude. To realize the promise of upcoming surveys, we need new approaches. Next decade cosmology needs next decade methods. I've given you a couple of examples. A parallel track that we're working on in the group is to develop new methodology that uses machine learning and a rigorous statistical framework to go beyond approximate likelihoods that everybody has been using in cosmology so far, to do likelihood-free inference that's based on forward simulations. But that's an entirely separate talk, so I'm not going to get into that. But I'm happy to discuss this, of course, over coffee.
Okay, so non-linearities are propagated and we're running late by 15 minutes. So maybe we'll have a quick question if there is one. Over there? Okay, Rahul has...
I think I propagated it linearly.
Well, so we'll have a couple of questions from Rahul and maybe next from Suhrud, and then we'll just move on to coffee and we'll have to come back quickly.
So you mentioned that one of the problems of these forward approaches is that essentially the statistical noise on your data is much smaller than the systematic noise and your essentially bias density relation is, right? And you were proposing the Alcock-Paczynski as a way of getting rid of it. And I guess that would make sense if the underlying observations were isotropic, but of course redshift space distortions make it anisotropic. And the way in which make them anisotropic also depends on the underlying galaxy-halo connection. So I was wondering how you actually dealt with that. I mean, it would look to me like you still have that problem of the bias.
So we do include redshift space distortions in the forward model. And they're included through the underlying density. So I guess they depend on this connection at a next order level. But because, I mean, they are a perturbation on top of a perturbation. But it's true that, that is correct. But we have redshift space distortions in the model. So we do actually fit an anisotropic model where the anisotropy is modeled through the redshift space distortions.
So I also wanted to ask about how much do we actually gain just from going to this approach compared to, say, just doing a simple Alcock-Paczynski with the galaxy distribution and then doing a cross-correlation to get the luminosity distance redshift relations for the supernovae. So whether the gain in doing the Alcock-Paczynski also with the supernovae, whether it's like how significant it is. Have you investigated?
So one, that's, I mean, for that particular case, I showed you the Fisher matrix predictions that are indicative, and I've told you that actually for our method, because I didn't want to have to explain why I think we can go to the very, very deeply nonlinear regime with this. So we actually truncated this, where is it? Oh, there it was. Here we go. We truncated this at K max of 1/2 or 1, which is in the moderately nonlinear regime. There are arguments that, again, I'm happy to explain why I think this can go to much, much higher K. In fact, supernova and galaxies are correlated at a very short distance. In fact, they're correlated at the scale of the size of galaxies, right? Because supernovae happen in galaxies. And so that trick is used when you do host identification for supernovae. Whereas here, because we're using structure, and I anticipated that some people might worry that maybe our model of the structure might be inaccurate, we actually truncated there, but I think we can go much, much further than that. But here's the point. So if you just use photoz's, actually a fairly optimistic model of photoz's for the supernovae, and you do your DLZ test, you get this contour. and then depending on what cutoff you prefer, you get either this or this when you include when you do this cross correlation approach. So it is a very significant improvement. Yes. Okay, but what I'm saying is that you don't need. I mean, that doesn't add because the supernovae are correlated to the galaxies. You're correlating in DL and redshift, and that is all the cross correlation. I mean, there's nothing in addition. You can use the fact that you have. I mean, you can use the photos, the information, but it's much weaker, so it's not going to change these constraints. Yeah. Yeah. Oh, yeah. Mm-hmm. Right, so there's going to be a noise term that will come in through the lensing on the supernovae, but typically there's going to be symmetric. So it might add noise, but it's unlikely to skew your results.
And we are really running late, so we'll take a break. So let's thank both Dick and Ben, and